Try again. Hi, and welcome to the next video in the series of videos about how to complete the hashing project in our class. In the previous video, I talked a bit about how hashing works in general, and particularly how the linear probing algorithm, as described in the Zybook, works. In this video, we're going to walk through the code that you were supplied for the starter program in the this project, and we'll go ahead and actually show you the places that you need to fill in and talk about the code that is there and try to explain what it does. So I'm going to share my screen and we'll get started. Okay, you should see the Replit web app here, which is the online IDE that has the hashing starter.py opened up. This is the program that you use to start the project. It's actually a complete program. It'll run. It doesn't do much of anything except spit out a couple of statistics, but you can prove to yourself that things are running just by running initially before you make any changes. I'm going to explain a little bit of stuff at the top. Then I'm going to jump down to the bottom to the main program, which logically is where the program starts. So, and then we'll go kind of top down through what the main function does back up into the classes and objects that are being used. So on line 3 and 4, those are the modules, Python libraries, if you will, that need to be imported to make the magic read of the JSON work. That's what load JSON does. And that's how it's able to read a file in JSON and convert it into a list of objects, which will be much easier for us to use and save us all the trouble of actually trying to read and parse that file line by line. Time is there because time is used to time some of the operations so we can get some statistics about the performance. And I don't think import assist is actually used at all here. So in your version, which I've already changed this version, but I'll change it back. In your version, it says this, table size, well, it says equals 100 and 10. And that's ridiculous, really. That was what value I had for testing. I made a very small hash table and I filled it up. But realistically, since there are over 4,000 items in the JSON file, we ought to make a bigger hash table so we won't have instantly fill up from collisions. So let's change that to the number 5003. Now I picked that number because it's a prime number and it's a little bit bigger than 4,200, which I think is the actual number of items in the JSON file. So although we will still have collisions, because that's a natural part of the hashing algorithm, the table won't fill up. So we won't be stuck being unable to eventually find an open bucket. So go ahead and make that change in your code right off the bat. Okay, now I'm going to scroll down to where the program starts logically, which is in the main function beginning at line 90. So on line 93, that's where the creation of the list of objects happens. That's where the JSON file gets read. So it reads stops.json and it puts it into a list of objects. So it goes through the JSON file and all those tags and values that are in JSON get converted into attributes in objects, and then the objects are put in a list or an array. Very handy because all of the file handling and parsing we don't have to think about. After line 93, we have a list of objects that we can use to insert into our hash table and to search for in our hash table. On line 96, we actually instantiate the hash table. We create an empty hash table. So actually on line 96, the hash table in yellow there in caps is a constructor. Now, if you come from a Java background, which I think a lot of you do, you're probably looking for the magic keyword new so that you can see that something's being instantiated. But in Python, to run the constructor, all you really have to do is give the name of the class. So the hash table is a local variable, which is an instance of hash table, which is basically an array of 5003 hash buckets. Lines 99 and 100 are just some statistics we can use to make sure that our results kind of make sense. We're debugging. It's always good to have some counts and see if they match your expectations. Line 104 is paired with line 110. That starts and stops a very fast timer, a nanosecond timer, that enables us to have pretty high resolution in how much time elapsed while we were, how much time was taken up by inserting things into our hash table using our algorithm. So that's kind of handy to have, and we print that out. So what you need to write, to create, to add to this, to get started, are really just three functions. You need to make that change to the number of items to 5003, but other than that, on line 43, there's an empty function definition called compute hash bucket. That needs to return a bucket number by performing the hashing algorithm on a string key. What string key? The 4-digit string that names the bus stop, like 9803. And what we will get out of that won't be 9803. It'll be a number between 0 and 5003 that corresponds to the hash bucket where we should put that key. Now, how the actual hashing algorithm is pretty simple as far as computation goes, just to get the bucket number. I'm pretty sure that's in the Zybook, but I'll give you a quick peek if you want to see what it looks like in my more complete program here. And you can see line 42 there. It's pretty simple. It's going through the key, the string key, character by character, and it's taking ASCII value of that character, and then it's modding that by the number of buckets to make sure that stays within range. It doesn't go outside the hash table. Now, in fact, you may not have thought much about the idea of adding up characters because they're letters, not numbers, right? Well, no, actually they're numbers. C programmers know this because in C it's readily apparent that a char, char variable, is just a small number. But in other languages, we think of strings as completely different from numbers. But each character you have, like A, B, C, those all have numeric values. And we can add up those numeric values. For instance, a 0, the letter 0, actually is number 48. So if you're computing a hash key on a string that contains a 0, it's going to add some numbers plus 48 plus some other numbers. So that's pretty well described in the Zybook, and I think you'll be fine there. So write that function and test it out. You can test it out just by running it on a bunch of the data from the buses from the buses JSON file, from the object list that you have, and dumping them out and see if different keys are getting different bucket numbers. There will, of course, be collisions, but you can at least prove to yourself conceptually that it's working. Line 49 is another function you need to write. That's the insert function. That's the function that takes a string key like 9803 and a value string like Keller Road and inserts them into the hash table at a location where they can be found in the future. The insertion algorithm is described fully in the Zybook in 434, at least in pseudocode form. But just to talk through it, it's got one really easy case. Sometimes, often we hope, after you compute the bucket number from compute hash bucket, you'll just go to that, your code will go to that bucket. There'll be nothing in it. It'll be none. This value will be none. You can put your key and value in there and you're done. Other times, of course, you'll go to the bucket number and there'll already be something in that bucket, some other key hashed to that bucket. That's called a collision. To resolve that, we're going to use the linear probing algorithm. And that algorithm's pretty simple. It just says if you're a bucket 202, that's the right bucket for your key, but there's something already in it, try 203. If there's something there, try 204. When you hit an empty bucket, just put your value right there. Now you've got the right bucket. So you're basically just choosing in a linear fashion successive buckets to the one that you initially chose until you find an empty one. And there's some pseudocode in the Zybook for that I think you can readily transliterate into Python, because where there's a while loop in the pseudocode, there'll be a while loop in Python. Where there's an if in the pseudocode, there'll be an if in your Python. I think it's pretty straightforward. Not to say you won't trip up on some Python details, but logically, I think it's going to make a lot of sense to you. Notice that we are, and among the things we put in the bucket is not just the value. Usually the zybook just shows the value, which is almost always a number, not a string, in the bucket. But we're going to have to also keep the original key. So if we hash the key 9803 to bucket 202, and that's empty, we can use it, we'll put Keller Road in there as the value, but we'll also keep 9803, those letters, as the original string. We need that on the search function to ensure that we got the right bucket, given that actual hashing can collide. Two or more things can end up in the same bucket, and the only way to know that you got the right one is by matching the key you're looking for with the key that's in one of the bucket you went to, the bucket number, or in one of the buckets you found when you started a linear probing from there. So that function, to take a quick peek at it, a more complete solution, is here. Let me drag this over. And there it is. It's not very long. It's from line 51 to line 66 in my case. And it's straight out of zybook 434, just translated into Python. You use compute hash bucket to get the bucket number. You go in a while loop comparing the bucket that you're seeking, checking if the key is nothing. Good, you're done. You can put it in there and you're out of the while loop. If there's already something in that bucket, then there's a collision, which is counted on line 59. And the while loop takes you back around to the next bucket. So it's pretty straightforward. So hopefully that's going to work well for you in your code, or your version of that's going to work well. Once you insert all the values into the hash table, you need to be able to see if you can find them. Can you search for them? Because one of the advantages of hashes is they're fast to search. So because they're order 1 or big O1, because the search time doesn't depend, at least not directly, on the number of items in the hash, because the hashing takes care of that. You do have some time spent in resolving collisions, but that's not going to grow as the size of the table grows. Search linear is a function that takes a key and finds the appropriate value. So it hashes the key to get a bucket number, goes to that bucket number, and then compares the key in that bucket to the key you're searching for. If they match, that's right, you find it, and you return the value, like a street name or stop name. If they don't match, using linear probing, you go down to the next bucket, check that one, the next bucket, and check that one. If you hit an empty bucket, that key's not there in the table. So eventually you either find an empty bucket, meaning it's not found, or you find a bucket where the keys match. That's the algorithm. And I don't think you're going to have a great deal of trouble coding it. It looks like the one implementation, not the only possible one, looks like this. So this looks a lot from line 73 to 77. That's the search. Looks a lot like the insert from line 54 to 59, right? Because they both use linear probing. They both look at the bucket. If they don't find it, they go to the next bucket, and so forth and so on. So pretty straightforward. So you've got to write those three functions. Once you write those three functions, you can go back down to main and use those functions in a test. And you're already using insert. It's already coded to use insert, which currently does nothing. You can also code a loop that searches for, I don't know, at least minimum 5 keys and see if you find the right values. That shows that your linear probing is working correctly. So that's the basic idea. And of course, I'm open to questions or comments if you need to have them. I'm hoping this will get you started in the right direction with doing the implementation, and I will see you in the next video.